Okay, all right, interesting. So, it looks to me like we're probably gonna need to make some kind of a substitution, right? So, and we probably have to play with it for a while to see what we come up with. Did anybody have an idea? Let's do this together. Did somebody come up with something that worked well for them?
I did this a couple of days ago.
Okay.
I think I did, for substitution, I did like square root of 4y squared minus 1.
Okay, so you were gonna say, we're gonna do that whole thing, like this?
I did this a couple of days ago, but I think I did this.
Okay. And then, we're gonna, did you next find the derivative, or what did you do next?
I guess like the substitution, so just found like what dy is.
So you found the derivative first, okay? And I think that we can see that an issue is gonna come up here, right? We're definitely gonna have an issue here. But this thing we could write as 4y squared minus 1 to the 1/2, right? So finding the derivative, we'd have 1/2 4y squared minus 1 to the minus 1/2. Then we would multiply by the derivative of the inside, right? Because we've got a chain rule going on here. Okay, so let's see. Then we'd have 8y, right? And then dy. And what's the good thing about that? Just to hold on for a second. That puts all of u right here. Okay, so if we get dy by itself, then dy, this is on the bottom, right?
Put square root over it.
Maybe du over.
Yeah, so if we multiply it on both sides, it'll wind up on the top. So we have, and so will the 2, right? Or we can just make that a 4. Why don't we simplify this thing before we move on? So, and we're in investigation mode right now, right? We're just going down rabbit holes till we get where we want to go. So the 2 and the 8 are going to make a 4y. That's on the bottom, so we can, write it square root 4y squared minus 1, and then dy. Okay, so now, if we solve for dy, then these things flip, right? So we wind up with dy, and we'll have du. That square root of 4y squared minus 1 will be on the top. So we'll have square root 4y squared minus 1 over, now we're going to have 4y on the bottom, and then du, right? Okay, so you want to try to give that a try? Let's forget about the limits of integration right now, and then just see what happens. Okay, so dy is all of that. The dy is going to be square root of 4y squared minus 1 over 4y, okay, and then du, right? Now, what do I have on the bottom? I got a y and a u. Got a y and a u. Okay. Okay, so I would have integral.
Could you also go ahead and substitute the top for u as well of the fraction, the square root of 4y squared minus 1?
Okay, so we'll look and see what happens there. Okay, so I'd have a u. Now that 4y is going to come down here and be with that y, right? So I'll have 4y squared, I'll have a u, and then a du. Now I still have a problem, don't I? I got a 4y squared. Any ideas?
I think what I did, this is the weird thing, was I saw, we did that equation there, for
Okay.
y squared.
So if we square both sides, then we have u squared equals 4y squared minus 1. Then solve for y squared. So we'll add 1 to both sides. So we'll have u squared plus 1 equals 4y squared. Then we'll divide both sides by 4. And we have y squared equals u squared plus 1 over 4. And now I got a bunch of u's, don't I? So we got there. So let's see. We've got u, we've got 4, we've got u squared plus 1 over 4, and we've got u and then du. You did great, you did great. We got there, and that's kind of the whole idea, right, in this, is to get there. So now let's see what we got. We've got integral. Okay, those u's are going to cancel, and those 4's are going to cancel. So I've got 1 over u squared plus 1 du. I think we can find a formula for that. We still have an issue though, don't we? We need to get our limits of integration on there. We either need to do that or substitute the y back afterwards, right? We do one or the other. We either substitute our limits of integration now and then just leave it as u and solve it out, or we substitute the y's back and use our original limits of integration. It doesn't matter. Either way is fine. Just for practice, let's go ahead and substitute our limits of integration now. Okay, so u of 1 will be, so now u was the square root of 4 over y squared minus 1, right? So u of 1 will be the square root of 4 times 1 squared minus 1. So u of 1 is going to be the square root of 3, right? And then u of the square root of 2 over 2. So u of the square root of 2 over 2 is going to be the square root of 4 root 2 over 2 squared minus 1. So u of root 2 over 2 equals, okay, so now that's going to be 2, that's going to be a 4, the 4's are going to cancel, so I'm going to have 2 minus 1, that's going to be 1, square root of 1 is 1. Okay, so 1 to the square root of 3 is what we're doing now. Now, does anybody recognize that integral right there? I mean, it's like, darn it, if that was, you know, just u by itself, then it would be a log. If it was u squared by itself, then I could do it as a u to the minus 2 and integrate, but it's not. Does anybody recognize it? I think it is arctangent. Very good. So what we have here is inverse tangent u evaluated from 1 to the square root of 3. Now, if you don't remember that, not a big deal. Do this. Google it. Get on your phone or computer or whatever you want to, and Google integral 1 over u squared plus 1. Okay, good. So now, here's what we got to do then. So we got to find the arctangent of the square root of 3 and subtract from that the arctangent of 1. Okay, well, we need to be a bit familiar with what the tangent function looks like. A couple of things we could do. We could look at a unit circle. We could also look at the graph of the tangent function. I didn't need to go out that far, did I, for a tangent? Because tangent has asymptotes at minus pi over 2 and pi over 2. Now, the inverse tangent is only defined on the interval from minus pi over 2 to pi over 2 because inverse functions have to be 1 to 1, right? So we only take one cycle of the inverse tangent function. That just means that it's only defined on that interval right there. So we look at this and we say, okay, the tangent function is negative between minus pi over 2 and 0, fourth quadrant. It's positive in the first quadrant from 0 to pi over 2. Okay, so those are both positive. Remember, when you find an inverse function value, that right there is a ratio. And what you get back is an angle, right? What you get back from an inverse tangent function is an angle. So here I've got a ratio, and the whole thing is an angle. So that's what I'm looking for, is angles, right? Okay, so I'm looking only in the first quadrant, so I need to know where the tangent function is the square root of 3. Okay, so now let's do this. I've got an angle theta somewhere in the first quadrant where the tangent function is the square root of 3. That means that the opposite is the square root of 3, and the adjacent is 1, and we know that one, right? 1, 2 square root of 3 is that one, and what does that make that angle right there?
Pi over 3.
Yeah, pi over 3. Very good. Okay, so we got that one. Now, inverse tangent of 1. Well, I mean, the only way that the tangent can be 1 is if the sine and the cosine are the same, right? And the only place that the sine and cosine are the same in the first quadrant is at pi over 4. So we've got pi over 4. We need pi over 12 to get common denominator. So we have 4 pi over 12 minus 3 pi over 12. So we have pi over 12. And I think that ought to work that problem. Is the next one similar to that? Like it's got a weird substitution like that?
I think so. I believe so.
Well, give it a try now that we've worked this one. See if something works out. The
Okay.
whole key here was, I'm sorry, tell me your name again.
Allison.
Allison figured out that something had to be done with that whole thing right there. So that's what she said. Let's let that be our U. And then realized, okay, well, you know, I have an issue towards the end, but when she just hammered through all those substitutions and all that algebra, she got this this y square and said, well, okay, can I deal with the y square from my original substitution? And yeah, we can, just by solving for that y square. And then the only other variable we have is u, and that's what we're looking for, is just stuff with u, right? So good job. Okay, any questions at all? All right. Oh,
Yeah, smile.
yeah. All right, here we go. Okay, so any other homework questions we want to look at?
Number 11, can I just show you, because it has a graph, and I'm a little confused about how it wants us to set it up through Pearson. Because it wants you to pick how you set it up.
Okay, that's interesting. Okay, can you tell me what the functions are?
X equals 24y squared minus 8y cubed.
Minus, how much?
8y cubed.
Okay.
And then the other one is x equals 6y squared minus 18y.
Okay. So when we graph those, you know, we could go through the process of doing all this, but apparently in this problem, the objective of this problem is not for you to, I don't know what the objective of the problem is, actually, to tell you the truth. It may be to do the whole thing. I don't know.
I think it just wants you to go through the steps, but the way that it.
So it's trying to lead you through the steps,
Yeah.
maybe? Okay, maybe help you to not make an error somewhere and go, oh crap, I don't have any of those. I need to go back and look at what I'm doing. Maybe that's the objective. Okay, so let's do that then. So, and it gives you the graph right off the bat.
Yes, sir.
And may I look at it, please?
You can just-
Thank you very much. Glad I didn't drop your computer. All right, so it tells us. Oh, and you can. It's not touchscreen, or is this touchscreen?
It is a touchscreen.
Oh, okay. It lets us zoom in some. Like how much?
I think you can zoom in on the screen as well, if you like. There you go.
Okay, it doesn't give us a ton of detail though, does it? But the important detail that it gives us is that it. Oops. Okay, the important detail is that it goes from 0 up to 3, right? That's the important detail. And then another detail, so we have a look like this and a look like that, right? And here we have x equals 6y squared minus 18y. And here we have x equals 24y squared minus 8y cubed. Okay, good. All right, thank you. Now, that's 3. And we could have figured that out, right, by setting these things equal to each other. Now, remember when we talked about this last time? We said, okay, you gotta look at the thing and decide, if I stack rectangles left to right, is it consistent throughout that I have the same function on top and the same function on bottom? And what's the answer to that question? Yeah, no, that's a big no, right? So then I start thinking about, well, I can think a couple of things here. I can think, well, maybe I need to break the thing up into pieces. I could do that. But then I got another problem here because I have this exact same one on top and bottom, and that's not gonna work. So then I start thinking about, well, what if I stack my rectangles left to right, up and down instead of left to right? Then do I have the same function on the right and the same function on the left every time? And yes, we do, throughout the whole thing, right? So I can draw myself a representative rectangle here. And it would happen at some y sub I. And it would have a width of delta y. Okay, now, if I was to find the area of that one particular rectangle, it would be whatever that right side value is minus the left side value. There we go. There's the length of that thing. The width is delta y. So there's the area of one of them, but I need that expressed as function values, right? Not words. So this one particular area would be, okay, so what's on the right? What's on the right is that 24yi squared minus 8yi cubed minus the one on the left. Now, if I don't get my parentheses in there, then I got a problem, because I won't have the pluses and minuses right now. So here's my question. The first step. So you got steps to go through here?
Mm-hmm.
What does the first step look like?
It wants you to set up the integral. And
So
you choose-
we're all the way to the integral on the first step. Okay, good. So there's one of these, and we can simplify this thing a little bit. 24yi squared minus 8yi cubed minus 6yi squared plus 18yi delta y. We can combine those two terms. So we have our rectangle, and we put them in order, I guess, if we want. And so we're going to have minus 8yi cubed plus 18yi squared plus 18yi delta y. That's one. We need a bunch of them. N of them. And that would get us an approximation of that area, right? So sum I equals 1 to n minus 8yi cubed plus 18yi squared plus 18yi delta y. Okay, that's an approximation of the area. To find the actual area, we would have infinitely many of these rectangles. So we would let the limit as n goes to infinity, and then this sum, 1 to n minus 8yi cubed plus 18yi squared plus 18yi delta y. And then that we can express as an integral, right? So now our area is gonna be the integral of minus 8y cubed plus 18y squared plus 18y dy, and we are stacking bottom to top. The thing starts at 0, tops out at 3. So now, Lily, is that the answer to the first question?
Yes.
Okay.
So,
I like it when I get stuff right. Now, do you need more assistance through this, or does that give you
I think that's.
an idea of how? Okay, all
I
right.
think it was just kind of confusing me because of the options it gives you.
Yeah.
Because I didn't know if it wanted the equations separated or if they wanted you to go ahead and simplify the subtracted.
Oh, right.
But I think it wants you to simplify.
Okay. Yeah, and that's something that you would. That's something that learning the software, that's going to be an issue for a little while, and then you'll start to figure out that it'll be consistently asking the same thing. You'll figure that out, and then by the time you take a quiz, you got all that worked out. Hopefully, on the test and all that, it'll be worked out. Okay, I want to make a comment. Something that I do after a test is I allow for corrections, and it the intention is that you would take a chance to reflect on your work, and then there's multiple intentions. So let's talk about those. Reflect on your work, really, really important. When you make an error, go back, see where your error was, realize what maybe you didn't quite have the concept completely together on, correct that. Now you've learned a ton by doing that. But on top of that, you guys, like I've said, you're going into a really hard job. You've chosen a hard life. And one of the things that you're gonna have to be able to do is communicate your technical ideas to non-technical people. After you leave college is not the time to work on that. You work on that now. You get to, you improve your technical communication while you're in college. So, what we're gonna do, and I'll have an example that I'll show later after the first test, but to let you know how this is gonna work. You're gonna, if you want to participate in the test correction process, then you're gonna look over your work and you go, this is where I messed up. Okay, then you're gonna write me up in, it's gonna be a Dropbox, and you'll do it in there, and you'll use the equation tool in eLearn to do this. And you'll say, okay, this is what I did, and here's where I made my error. And this will be well said. You'll be communicating this very well, so that if somebody, has maybe a knowledge of calculus, but doesn't have to read your mind, right? Because I can't read your mind. Then you say, this is what I did. Here's what I should have done. And then you use that tool, and that's the another objective of this process. No matter what job you go into, you're going to use software. You're going to be using a computer, and it'll probably have a technical component to it because you're going into a technical job. And so you'll need to be able to utilize that software. So you're going to use the equation tool in the Dropbox to finish out this process of explaining how you should have done it. And you'll do the whole thing. I won't have to guess what your thoughts were anywhere. If I have to guess what your thoughts were, I can't give you any partial credit. Now, this will be partial credit, but the only way, I'm having to change something up because I think we got to a point where, and this is human nature, we got to a point where people were kind of resting on the partial credit to squeak by. I'm only going to look at them if you're not missing any homework problems, because this has everything to do with effort. not missing any homework assignments, not missing any quizzes, and you've done the test review completely. If those things are done, then that test correction thing can be very beneficial to you. If any of that, if you're missing any homework assignments, missing any quizzes, then that tells me you just didn't prepare for the test. And you know, anybody can go look up how to work a problem and then write it up. But if you don't prepare, if you're not going to put that much effort into it, I'm not putting any more effort into it than that. So, good. Everybody understand? Everybody feel good about that? All right. Any other homework questions before we move on to what we're going to do today? All right. What we're going to do today is similar to what we've been doing here. Kind of a similar concept. We're going to be finding volumes rather than areas. So, let's say, no, I don't want it to look like that. I've got a bucket. We're pirates. And we have a bucket of blood. They're always singing about buckets of blood. All right, and this blood's been around for a few days. It's congealed, and we've got this pole, this kind of a pole kind of a thing that sits down. It actually it's attached to the bottom of the bucket there. Okay, and this bucket is full completely with our congealed blood. And this pole has attached to it a triangular wiper like this, okay? And there's a crank on the top, making this up as I go along. And you turn it a 1 revolution, and what's gonna happen? Well, the little wiper here is gonna come around like this, and it's gonna take some blood out for you to put in your bowl. Okay? All right, and what shape would that blood be in?
Cone.
You'd be a cone, wouldn't it? You'd just sweep out a cone. Very nice cone, as a matter of fact. If we, have a good seal on here at the edge. Let's say that this bucket is 3 feet deep. And this wiper here, the height of this wiper right here, let's say that that's 1.5 feet, okay? And the radius of our bucket is 2 feet, okay? I could draw a picture of that cone, couldn't I? It'd look like this. It'd have a height of 1.5 feet. It'd have a radius of 2 feet. I'll tell you what, dude, let's just do this. Let's Google the formula for the volume of a cone, please. Let's do that. See what we come up with.
Pi radius squared times the height divided by 3.
Okay, so 1/3 pi r squared h. 1/3 pi r squared h. Okay, so let's plug that stuff in here. So that volume would be 1/3 pi 2 squared times, we'll call that 3/2, okay? So let's see, what do we got here? Oh, okay, that's I did not intend for this to happen, but it's kind of cool that this happened. That 2 is going to cancel with one of those 2's, right? Those 3's are going to cancel. We got 2 pi. 2 pi what?
2 pi feet cubed.
Cubic feet, very good. Yeah, because that is feet squared and that's feet. And that makes sense because volume should be a cube, right? Okay, so 2 pi cubic feet. All right, well, let's see if we can think about this in less of a pirate way and more of a calculus kind of a way. That could be my wiper right there, couldn't it? And I could put it right on the, right at the origin right there, the bottom of it on the origin. And the rotation of that wiper would mean I'd rotate about the y-axis, right? Okay, so let's think about this for a second. That point right there would be 1.5 on the y-axis, right? What would be the coordinates of that dot right there? 2.
1.5.
Yeah, very good, very good. All right. So could I find the equation of that line? I think I could. I mean, I'm going up 2 to the right 3/2, right? So, because I'm from here, from 0, 0, I'm sorry, I'm going up 3/2 and to the right 2, right? So that'd be 3/4, right? That'd be the slope of that line. And what's its y-intercept?
0.
Yeah. So the equation of that line would be y equals 3/4 x. Okay, now let's think about something. If I was to rotate that thing around, once I got 180 degrees around, so let's think about when I get to a half of a rotation, I'd be over here, wouldn't I? It would look exactly the same over on the other side. And if I was to draw a representative rectangle, just like we do with those areas between curves, I'd have that right there, wouldn't I? Let's see. That'd be delta y would be the width of that rectangle. This is exactly like we did before, isn't it? Where is it? It's at some yi, right? Now, if I rotate half a turn, that rectangle comes around and I'm right there, aren't I? Now, if I was to look down on the top of that thing, what would it look like? So if my eyeball's up here, and I had a kind of a hard night, what do I see?
A semicircle?
Well, if I rotate all the way around,
Circle.
I'd see a disc, wouldn't I? Because it would have a thickness. It would have a thickness of delta y. Okay, so let's draw that disc right here. So there's that disc. And that disc would have this thickness here of delta y, right? Let's see. What would the radius of that disc be? I think it'd be whatever.
1.5, the radius of the cone.
Well, but it changes, doesn't it? As we go from the bottom to the top, it changes. Would the radius be the distance, the x distance from an axis, or the y distance from an axis?
Yes.
Yes, x, wouldn't it? It would be the x distance from the vertical axis, wouldn't it? The radius would be from there to there. Okay. Well, it's just whatever x would be whenever y was whatever it is, right? So just x sub I. But I see a problem. Do you see a problem? My width is in what form? What variable?
Y.
Yeah, delta y. And my radius is x. So what would you do about that if you were you? What did we do when we used, when we did the area thingies?
Just solve for x.
Yeah, pretty much, huh? Yeah, I can make, that's the equation of that line. I can figure out what that x is in terms of y. I can go up to some y value and figure out what the x value is there, right? I can do that. Okay, so I'm gonna multiply both sides by 4/3. So x sub I is gonna be 4/3 y sub I. Okay, I like that better. Okay, that'd be one disk. What if I had a bunch of them? What could I do? So let's do this. Let's figure out what the volume is for this disk. How do you find the volume? It's a right circular cylinder basically, isn't it? It's just short. It's like a can, but it's short. So what's the volume of a right circular cylinder?
Pi r squared times the depth of it, or?
Yeah, it is, isn't it? It's pi r squared. It's the area of the face times the depth. So pi r squared h. Well, the h is our delta y, right? Because it's a real short can. So here we go. So I could express a volume of one of those disks as v sub I equal to pi r squared. Okay, so r is 4/3 yi, isn't it? Squared delta y. Now, is everybody following along well here? Okay. Now, that's one. If I stacked a bunch of them, I could approximate the volume of the whole thing, right? Okay, so the volume of the whole thing could be approximated by adding up n of those disks stacked from bottom to top. Okay, so pi. I'll tell you what I'm going to do. I'm going to go ahead and call that 16/9 yi squared, okay? Delta y. I could express the volume exactly if I had infinitely many of those. Okay, so the volume would be expressed exactly as the limit as n goes to infinity, sum I equals 1 to n, pi 16/9 yi square delta y. But that's going to be an integral, isn't it? That's just like our area thing, except we're doing volumes instead of areas. Okay. Let's see what that looks like. Now we're going to have to get some limits of integration, right? Am I stacking left to right or up and down?
Up and down.
So will my limits of integration be x's or y's? They'll be y's, right? Yeah, the other x, y, yeah. Okay, so here we go. Where does it end? It starts at 0 and ends at, yeah, 1.5. Very good. So we'll go 0 to 3/2. Pi 16/9 y squared dy. Okay, so let's see. You know what? I'm going to pull this 16/9 and pi out here like this to make it easier for me to look at. So this is what I'm integrating right here. Is everybody following along okay? Does anybody want to go back and look at any part of this? It's really important that we're able to visualize what we're doing, because you're going to do a lot of that, and follow along how we're building up our integral here. Okay, so we have 16/9 pi. This is going to be 1/3 y cubed evaluated from 0 to 3/2. Is anybody nervous? Because better turn out to be 2 pi, right? Let's see. So that's going to actually be 16/27, isn't it? Times pi. And then I'm going to have 3 halves cubed, right? Minus 0. So let's see, we got 16 over 27 pi times 27 over 8. The 27s are going to cancel, and the 8 and the 16 are going to make it 2, so we get 2 pi. Good. That's what we expected. That's what we hoped it would be, so that I wouldn't look like an idiot. Okay, any questions? Okay, this is it, man. This is what we're going to do. We're going to find volumes of revolution. This is, I believe, section 6.1 and 6.2 in your book. This is a relatively new book for me. I've only used it one semester, so I used the other one for years, so I'm not dead certain on those numbers. Yes, ma'am?
Is it, you said that it was only going halfway, would it be half of that volume?
No, it went all the way up, from 0 to 3 halves. Did I say it's going halfway somewhere?
You said that it was rotating half of the way.
Oh no, I said, what if we rotate it halfway, what would you see?
Oh, okay.
That I was trying to point out. Okay, let's go back and clear all that up. Okay, so I said, well, let's draw a graph of this piece right here that we swept out. And then that was this right here. Then I said, what we're going to do is we're going to rotate it just like we did that. Now, if we rotate it halfway, what would that look like? And it would look like this right here, right? Just so we could get what the other extreme looks like. Yeah. But yeah, if we rotate it halfway, what do we get? We get pi, right? Yeah. Okay, good. Any questions? Yes, go ahead.
The i's just represents the fact that the equations you're dealing with are related to the
Well, so here, let's do this. Do you remember when you did Riemann sums? So let's say we've got, a parabola like this. Boy, I probably better draw it better than that to illustrate this. We have, let's say, a parabola that looks like this. And I want to know the area, let's say, up to this point. And I want to break it up into 4 pieces to approximate this area. Now remember when you did Riemann sums, you'd say, okay, here's x1, here's x2, here's x3, and here's x4. And that I just says whatever position, like it could be 1 or 2 or 3 or 4. If I have 4 of them, if I have 100 of them, it could be 1 to 100. But it's just saying someplace, just somewhere. Okay? Anything else? Any other questions? All right, let's do some more. Let's see. I tell you what, let's do. Let's rotate that thing about the x-axis. Let's take the same line, y equals 3/4 x, and rotate it about the x-axis and see what happens. So, starting with the same graph, y equals 3/4 x. I'm going to rotate it about the x-axis. Okay, now, so I'm going to come around this axis here. I'm probably going to drop a vertical to here so I can see what it looks like. Okay, if we rotate half a turn, what does that look like? Looks like that, right? And let's say that we're going out to the same spot here, so x is 2. So we're going out here to where x is 2. Okay, if I draw myself a representative rectangle. Okay, now if I'm going to rotate about the x-axis, I think my rectangle is going to go the other way, isn't it? To make a disc. So now it's at some x sub I place, right? And let's see, it would come around and it would be over here. And then if I rotated it, I would have something that looks, something like this. Could be drawn a lot better, but if my eyeball's over here now, then what would I see? I'd still see a disc, wouldn't I? Okay, but now this disc is gonna be a little bit different, right? This disc, rather than having delta y, it's gonna have a delta x. That width is gonna be a difference in x values this time because they're left to right. That width is left to right. Okay, the radius. Let's think about the radius. I think I'm gonna draw it this way to match my picture up here. Now is the radius a distance, a y distance from an axis or an x distance from an axis? It's a y, it's an up and down. It starts at the x-axis and goes up to that line. Okay, so this radius is gonna be some y value, y sub I. But I got a problem, don't I? I've got delta x right there, and I've got y right there. I need it to be x's, right? But that's not a problem, because I already know what the relationship is between y and x. Any y value right here I can find by just plugging in and figuring out what x is. Okay, good. So that's gonna be 3/4 x sub I. Okay. Volume of a right circular cylinder, pi r squared h. So the volume of one of those, as I stack them left to right, the volume of one of them is going to be pi 3/4 x sub I squared h delta x, right? So v sub I is going to be 9/16 pi x sub I squared delta x. So there's a very nice expression of what the volume of one of those discs would be. But I'm going to stack a bunch of them so that I can get an approximation of the volume of that whole thing as those radii get bigger and bigger and bigger. Okay, so we have the sum, I equals 1 to n, 9/16 pi x sub I squared delta x. But I don't want an approximation. I want an exact value. So I will find the limit as n goes to infinity. Sum, I equals 1 to n, 9/16 pi x sub I squared delta x. But that's an integral. So that volume, okay, now that I'm going to make an integral, I'm going to need some limits of integration. Now, am I stacking my discs up and down or left to right? Left to right. And they start at?
0
and end at? 2. Good job. So 0 to 2, 9/16 pi x squared dx. Okay, so let's see what we got. We got 9/16 pi times 1/3 x cubed evaluated from 0 to 2. Okay, so 9/16 pi times 1/3 times 2 cubed minus 0 cubed. So let's see what happens. Let's see, 2 cubed is 8, right? We got a 3 that's going to cancel. So do we wind up with 3/2 pi? Is that what you guys get? work out? Okay, any questions about any of that? We could check that, couldn't we? Go ahead.
The change in x represents d of x in
Yeah, so remember when you first started talking about Leibniz and the limits and then the talking about the differential as a function in Calc 1? You said, okay, if we're going to have a theoretical value delta x that could go to 0, then we have to treat it as a variable function dx. Yeah. So yeah, kind of. Okay, let's check that. It's just a cone still, right? It's still gonna make a cone. It's just, you know, we have to look at it a little bit differently. So it's a cone that looks like this. And let's see, its radius would be that distance right there, right? The top, that's 3/2 for that particular one. And then its height is 2. And the volume was 1/3 pi r squared h. So we have 1/3 pi 3/2 squared times 2. And we're gonna have a 2 left over, right? And one of the 3's is gonna cancel. So we're gonna have 3/2 pi. Yeah, so we're feeling pretty good about how that worked out. Okay, now I know what you're thinking. You're thinking, what if there was a hole in that volume? Okay, well, let's see what that looks like. So let's say that we're gonna take a different region now. We're gonna take the region bounded by y equals, do I make one up or do I find out one for sure? That works. Let's make it up, let's be dangerous. Y equals 2x minus 2. X equals 1 and x equals 2. Okay, so we're gonna take the region bounded by these 3 graphs, and we're going to rotate it about the y-axis. I probably shouldn't make these up, but let's just see what happens. Live dangerously. So I have a y-intercept of -2. Gonna go up 2 to the right 1, up 2 to the right 1, and that is that line right there, right? And then x equals 1 and x equals 2. And then I should probably say y equals 0 also. So that's going to be the x-axis. So what do we have here? We have this region right here is going to go around the y-axis. Okay, now if I rotate that a half a turn, let's just see what it looks like when I do that. Now, that edge of that triangle would come over and be right there, right? 1 unit away from the origin. And that edge would come over and be here, 2 units away from the origin. This thing is 2 units high, so that edge comes over and hits right there, right? So that is what we would see if we rotated a half a turn. Okay, so now let's make a representative rectangle. Okay, so right there, and that would be a delta y, wouldn't it? And up and down. Okay, now that after a half of a rotation would be over here. And when I rotate that thing, put my eyeball up here, what am I gonna see? What's that representative rectangle gonna look like when I rotate that thing? Well, let's see. So I'll rotate here, and then come around here like this. And what am I actually gonna see here? So it's gonna be like a washer, isn't it? It's gonna be a washer. So it would look like this. If you're in law enforcement, you might think it looks like a donut. But that's on the wrong side, isn't it? So there we go. I think that's what we would see. And I think that right there, yeah. Well, I've said it differently, haven't I? That's gonna be delta y, right? Now, the radius of that thing, well, I'm gonna have an outer radius, aren't I? I'll have an outer radius and I'll have an inner radius. I gotta figure out what both of them are. So I'll have an outer radius that'll go to there, and then I'll have an inner radius that'll go to there. I need to figure out what both those are. Because how would I find the volume of that disc? The whole volume of that disc. I mean, of that washer.
The volume of the outside minus the volume of.
Yeah, cut it out, right? I would figure out what did I punch out of there. So I need the big radius here. So I'm gonna do this in two parts then. So I'm gonna have the outer part. So let's figure out what that is. What's the radius of the outer part?
2.
When? 2, when?
The entire way.
Yeah, always, right? Yeah, 2 always, right? Except never, right? Yeah, it's always good. Yeah. Okay, good. So that outer radius is 2. Wow, that's pretty nice. That made it nice. Okay, good. How about the inner? So that inner radius. Now, is that a up and down distance or a left and right distance? So that's an X, isn't it? And what would it, so I might just call it, X sub I. Okay, but, what's the problem? What's the height here on the outer? Of the, like if I'm looking at it, looking down on it, what's the height? Yeah, it's delta y. That's not a problem here because I got a constant, right? It's still delta y though, isn't it? Here, and so I got a problem. My problem is that I've called that an x and I need it in terms of y, right? So what am I gonna do? Yeah, I think I'll go back here because that line right there is the relationship between x and y on that inner radius, right? The whole way. So really what I need to do is solve for x so I can express it in terms of y. So I'm finding y values from x values rather than x values from y values, right? Or the other way around. So we'll add 2 to both sides. So we'll have y plus 2 equals 2x. Then we will multiply by a half. So we'll have 1/2 y plus 1 is x. So that is going to be my radius for the inner part of that, right? Now I got a couple of ways I could do this. I could find two separate volumes and subtract one from the other, like over the whole thing, right? But I'm going to tell you that that's not going to be really convenient in the long run. I think what I'm going to do is I'm going to say, well, for every step along the way, every disc that I draw, every washer that I draw, the volume is going to be the outer minus the inner, right? And then I can just stack them up. So the volume of the outer is pi r squared h, right? So 4 pi delta y, right? Everybody good with that? Pi r squared h. Pi times r, which is 2 squared, 4. H is delta y. Okay? For the inner, the volume of the inner part of this washer, pi r squared h, so pi times r squared, so 1/2 y sub I plus 1 squared delta y. So that's the volume of the inner. Okay, so the whole volume, one volume, v sub I now. That's gonna be the outer minus the inner, right? So 4 pi delta y minus pi 1/2 yi plus 1 squared delta y. Now, actually, I could simplify that quite a bit, couldn't I? I can factor out a pi and a delta y from both of them. So I'd have v sub I equals pi times delta y. As a matter of fact, what I think I'm going to do is to keep it in order, I'm going to put the pi first and the delta y last. Okay, so I'll have 4 minus, now I got to put this in parentheses, right? Because this is a quantity squared. 1/2 yi plus 1 squared. Now, have I accounted for everything? Everything except the delta y, right? So I'll put that there. So I've got pi, got the 4, so there's 4 pi delta y. And then I got minus pi 1/2 y plus 1 squared delta y. So we're all accounted for. Now, what really happened here? So this is going to be up to you, how you do this. I go bit by bit to make sure that I don't blow anything, okay? You might look at it and go, well, it's pi, and then I've got the square of the outer radius minus the square of the inner radius, and then delta y. You can do that if you want. I don't usually, because I like to see it build. I like to see it go from the beginning to the end. And I like to make sense of it as I go. So now my volume, I can approximate by having a sum of these. Pi equals 1 to n, pi 4 minus, and I might start to multiply this out and see what I really have here, simplify this thing. So if I square this, I have to remember that I FOIL it, right? I don't square each term. So I have 1/4 yi squared plus 1/2 yi plus 1/2 yi, right? So plus yi plus 1 and then delta y. Okay, so I'm gonna come over here. So let's see now. I can distribute the negative. And I'm going to find a limit as n goes to infinity, right? So I might do that all at once. So my volume would be the limit as n goes to infinity. Sum I equals 1 to n. Okay, I've got a pi. I've got 4 minus 1/4 yi squared minus yi minus 1 delta y. So that would be then the exact volume. And now I can make an integral. So the volume would be the integral, and I need my limits of integration, right? So I'm stacking these things bottom to top. Where do I start?
0.
And where do I end? That 2, good. So 0 to 2, pi. Now I can combine the 4 and the 1, and I'm gonna write them in order because I like it that way. So minus 1/4 y squared minus y plus 3 dy. Okay, so let's see. This is gonna be pi. I can integrate each one individually. So I'm gonna have minus 1/12 y cubed minus 1/2 y squared plus 3y evaluated from 0 to 2. All right, so I know what you're thinking. You're thinking, you know, every time we've done this, we've drawn our representative rectangle perpendicular to the axis of rotation. And you're wondering, what if I drew it parallel to the axis of rotation? Okay, let's try that. And now, if I draw my representative rectangle parallel to the axis of rotation rather than perpendicular, shouldn't I get the same volume? I think I should. Shouldn't change it. Still rotating, same thing, same graph around the same axis. So let's see what that looks like. So I'm going to take this y equals 2x minus 2, has a y-intercept of -2, slope of 2, same line, same restrictions on the region that I'm rotating. So right there, rotating that around the y-axis. Half a turn, I'm there. Draw a representative rectangle. Now, what did we just say? We've been drawing our representative rectangle perpendicular to the axis of rotation. Now let's draw it parallel to the axis of rotation. I should have drawn this bigger, and I'm going to redraw it bigger. And here is our representative rectangle now. So that comes around and sits there when I make a half a turn. And now what does that look like when I rotate it? That's a delta x2, isn't it, by the way? And what happens when I rotate it? Well, let's see. That would come around to there. That would come around to there. That would come there. That would come there. And I'm thinking this thing is looking like a shell, isn't it? That's gonna be a shell. Like a spacer. You ever put a spacer between on a bolt between a nut and some other surface? Who's the car? Was it you? You're the car. Who's the car person that was in the room? Oh, that's right, Josh. Yeah. Well, you do a lot of that when you're working on cars. If you're doing like, you know, doing your own thing. So, it looks to me like though if I stack those shells out, I'm still going to wind up with the exact same volume, right? Still going to be the exact same thing. Well, how do I deal with that? Well, let's think about this. Think about the label on a can. If you tear that label on a straight line and then lay it out, what does it look like? It's a rectangle, isn't it? And it has thickness, although you just can't really see the thickness of the paper. You don't really appreciate the thickness of the paper, but this thing is still gonna be a rectangle with some thickness. So it's definitely gonna be a volume like this. And this right here is gonna be that delta X right there. Now let's think about the height of this thing right here. Wouldn't that be just this right here? At some X sub I? But what is it though, really though? It's a Y height, isn't it? Isn't it just Y? It's the distance from the X axis up to that point, that Y coordinate on that line. So it's a Y. But the problem is that our variable of integration is going to be X, isn't it? Okay. Well, Y is just 2x minus 2, right? So that's going to be 2xi minus 2. That'll be the height of the thing. What's the width? What's that going to correspond to?
Is that delta X delta X?
No, I'm talking about that width right there.
So is that the radius?
Not quite the radius.
Radius of the outside minus.
Has to do with the radius.
Is it
Circumference.
radius times 2?
Circumference, isn't it? When you take that paper label off the can and lay it out, the length of that thing or width or whatever is just it's just whatever rolls out when you take the circumference of the can and lay it out flat. So that's the circumference of that thing right there. What's the formula for circumference?
2 over pi.
Okay. And I need an expression for the radius, don't I? What's the radius? Well, it's the distance from here to here, isn't it? What's that distance? What's that?
X.
It's just X, isn't it? Yeah, it's just however far over there I went. It's just X. The distance from the Y-axis out to some spot on the X-axis. It's just some X distance. So I can express this then. I'll call it the length, okay? So the length of this thing is 2 pi x sub I. Now I can find the volume of that thing, can't I? So the volume, V sub I, would be length times width times height, but you know what we mean. So it'll be 2 pi xi times 2xi minus 2 times delta x. I mean, I don't think we blew it yet. I think we're good. So now, is this that 29 pi over 6? Yeah, so I'm gonna erase all that and then finish over there, okay? I'm gonna keep that. Okay, so let's see. The volume then can be approximated by a bunch of those. So we're gonna add them up. I equals 1 to n. 2 pi. I think it's gonna probably be to my advantage to multiply that out. So I'll have 2x sub I squared minus 2x sub I delta x. Now, the volume would be exactly then the limit as n goes to infinity. Sum I equals 1 to n, 2 pi 2xi squared minus 2xi delta x. That's gonna be it's gonna be an integral. Okay, now I gotta figure out, where do these shells start and where do they stop?
1 to 2.
Yeah, they do. They go from 1 to 2, don't they? So 1 to 2. So this is going to be the exact volume now. 1 to 2. You know, I could take a 2 out of there, couldn't I? I have 4 pi on the outside. 4 pi x squared minus x dx. And then I can integrate, so I have 4 pi 1/3 x cubed minus 1/2 x squared, evaluated from 1 to 2. So I have 4 pi times, all right, that's gonna be 8/3 minus 2. Minus, now I've got some value here that I'm gonna need to accommodate for. So 1/3 minus 1/2. Now, let's hope we got 29 pi over 6 out of all this. So we've got 4 pi. If I'm gonna combine those two, I'm gonna have to turn that into thirds, right? So 6/3, so that's gonna be 2/3 out here. Then on the inside, I can distribute that negative. So I'll have minus 1/3 plus 1/2. Did I do that right? So I have 4 pi times, let's see, so this is gonna be 1/3 plus 1/2. I have to turn that into sixths. So I'll have 4 pi times, that's gonna be 2 sixths plus 3 sixths. And we got 4 pi times 5 sixths. Okay, so we got a different number, didn't we? We got 20 pi over 6, which means that I made an arithmetic error somewhere. Did anybody catch it?
I think it might be like on the second from the bottom there.
Uh-huh.
You have like minus 1/2 times 2 to the 2. On the next step, you have like minus 1 over 2. Shouldn't it be just like?
It should be a 2, shouldn't it? Yeah. Okay, good. So that stuff I said earlier, forget that. From here forward. And let's figure that out. So this is minus 2/3 plus 4, right? And that is gonna be pi times minus 2/3 plus 12/3. That's gonna be 10 pi over 3. And so is that, 10 pi over 3. There we go. Okay? Any questions about any of that? All right, so we have 2 methods that we've talked about. Disc and washer are really the same. The washer is just discs with a hole punched out, right? So we have the disc and washer method. And then we have the shell method. With the disc and washer method, we drew our representative rectangles perpendicular to the axis of rotation. With the shell method, we drew our representative rectangles parallel to the axis of rotation. Okay? Yes, ma'am.
One question. What would happen if the axis of rotation wasn't an axis, but like a line of x equals 2?
You want to do that? Okay. I'm gonna let you guys do that. And that is a good question, because questions like that are totally gonna come up. You are going to see that in the homework. So let's do that. Now, the answer to that question is, you're not gonna do anything different. It's just that it won't be like when you eyeball it, you'll have to think a little bit more about these distances. Okay? So let's, as a matter of fact, so let's don't live that dangerously right now. Let me get one that I had planned to do like that, okay? To make sure we get numbers that work out nicely. Here we go. So we're gonna take the functions y equals x squared, x equals y squared, and whatever is bounded by those functions, and we're gonna rotate this about x equals -1. Okay, so take a second and draw the graph, draw the picture of what the rotation is gonna be like. Let's use the shell method. Let's go parallel to the axis of rotation. Wow. Really not very good at drawing these very clearly. Is that better? I guess. So, here's the thing. There's y equals x squared and x equals y squared, right? If I'm gonna rotate this around this axis right here, that point right there is 1 unit from that axis of rotation, right? So when it rotates around, it's still gonna be 1 unit away. That point up there is 2 units away from the axis of rotation. So once I rotate, it'll still be 2 units away. So I do believe that that's what that's gonna look like. And then if I use the shell method, I'm gonna draw my representative rectangle parallel to the axis of rotation. So this is what we look like here when we complete that rotation. Okay, so if we break that thing and lay it out, here's what we got. Is everybody doing pretty good here? Seeing it okay? Ooh, okay, that's a little different from before, isn't it? But what's do I have a width? Is my representative rectangle, is its width a delta y or a delta x? Yeah, it's delta x. We can see that pretty good. So that's that one. We're good. Height. So this right here, this dimension right here, what does that look like it is? Where does it start? Where does it stop?
Square root of x minus x squared.
Yeah, so it's the difference between those two y values, isn't it? It's the y value here minus the y value there. I believe that's what it is. Okay. X is gonna be my variable of integration. So I've got the y value here already expressed as x, right? I need that one. So I'll just go y equals the square root of x, won't I? Okay, so now it's the top one minus the bottom one. So this height right here is gonna be square root of x sub I minus x sub I squared. Does everybody feel pretty good about that? Okay, now. I need to know what the radius is, don't I? Because I got to get the circumference of that shell to make this length right here. Work on that for a second. See if you can come up with an expression for that in terms of x. Now remember, in every other case, we just said, how far is it, right? That's what you gotta ask yourself. You gotta look at it and say, how far is it from there to there? So now, looking at this little representative rectangle, that's x sub I right there, isn't it? That's just some x value. And there will be like a bunch of them from here to here, from 0 to 1. Be a bunch of them in there. But what's the distance between that and the axis of rotation? Pardon?
Do you add one?
Yeah, you add 1, right? It's that far from here to here, plus that 1 right there. Now, there's a couple of ways you could think about that. If you were thinking about, say, like on a number line, there's -1, there's some x sub I value right there. How do you find the distance from a right endpoint to a left endpoint? You subtract them, right? So it's just x sub I plus 1. If you want to do it that way, if you want to think about it that way. I just like to look at it and go, well, it's 1 from there to there, and it's x to there. So it's x sub I plus 1. Okay, great. Now, let's build up our integral. So one volume would be just all that stuff multiplied together. Yes, sir.
I'm slightly confused. Wouldn't the length be the circumference of the?
Yeah, you're assuming I was through. Yeah, I blew it. 2 pi, right?
Okay.
2 pi r. Good. Yes, very good. Turns out I was the one that was confused. Okay, so here we go. We've got 2 pi x sub I plus 1 times the height. So that's going to be the square root of x sub I minus x sub I squared times delta x. Okay. Probably want to call that x sub I to the 1/2, right? And then do a bunch of multiplying. So, but we can go ahead and say, all right, our volume is approximately the sum I equals 1 to n. 2 pi. All right, let's see. We're going to FOIL this thing out, right? So we'll have x sub I to the 3/2 minus x sub I cubed plus x sub I to the 1/2 minus x sub I squared delta x. You guys get the same thing? And so now our volume is exactly the limit as n goes to infinity. Sum I equals 1 to n, 2 pi x sub I. Let's see, let's put these in order. So x sub I square, oh, no, cubed. Minus x sub I cubed plus x sub I to the 3/2, nope. Minus x sub I squared plus x sub I to the 3/2 plus x sub I to the 1/2 delta x. Okay, good. Now we can make an integral. Now, where do my shells start and stop? Yep, 0 and 1, right? Start at 0. They're going to start here and end there from 0 to 1. So that's how they're going to kind of build on each other, like those Russian dolls that pop out of each other, right? Okay, so we've got 0 to 1. We've got 2 pi minus x cubed minus x squared plus x to the 3/2 plus x to the 1/2 dx. Okay, what do we got? We got, this is gonna be 2 pi minus 1/4 x to the 4th minus 1/3 x cubed plus 2/5 x to the 5/2 plus 2/3 x to the 3/2 evaluated from 0 to 1. Okay, everybody doing okay? Any questions? All right, so, well, let's see. That's a bunch of zeros, so we just gotta worry about the 1. So that volume is gonna be 2 pi times minus a fourth. Now, times 1 to the fourth, so 1. Minus 1/3 times 1 plus 2/5 times 1 plus 2/3 times 1. We're gonna need, what are we gonna need here? 60ths? To get ourselves a common denominator? I think so. Okay, so 2 pi times, we could make it a little simpler to start off with, but let's just go ahead and do it. So we'd have minus 15/60ths minus 20/60ths plus 24/60ths plus 40/60ths. So we have 2 pi times, okay, now what do we got here? We got 64, well, we got 44 minus 15 is 29. There comes that 29 again. Sure hope that's right. 29/60ths, which is going to give us 29 pi over 30.